Good morning, students. Today we are going to see how to produce induced EMF. So already you know what is EMF. EMF is electromotive force. Actually, electromotive force is not a force. It is the amount of work done in moving unit charge throughout the circuit. So EMF is basically energy to take a unit positive charge throughout the circuit. That is the reason why electromotive force is measured in terms of joule per coulomb or volt. You know, volt is the unit to measure potential or potential difference. Already we have seen what is called potential difference. So potential difference is the amount of work done in taking certain amount of charge from one point to another point in an electrical circuit. So electromotive force is not a force. It is the amount of work done in taking a unit positive charge throughout the circuit, and it is measured in terms of joule per coulomb or volt. So in this session we are going to see how to produce induced EMF. You know what is meant by induced EMF. So when magnetic flux changes with respect to time, an EMF is induced in the circuit. This EMF is called as induced EMF. So there are several methods of producing this electromotive force. Already we have seen it. So what are the methods of producing EMF? So methods of producing EMF. So what are the methods of producing EMF? One is electrochemical method. Electrochemical method. This electrochemical method is the method of producing induced EMF by chemical reaction. So this is the method how electromotive force is produced in cells, chemical cells. In lower classes you might studied about voltaic cell, Daniel cell, Lagrange cell. In all types of electrical cells, EMF is produced as a result of chemical reaction. So this is one method of producing EMF. The second method is thermoelectric devices. Thermoelectric devices are used to produce EMF. In thermoelectric devices, EMF is produced as a result of difference in temperature. So you might have already studied about thermocouple. In thermocouple, EMF is produced by maintaining two junctions at different temperature. The produced EMF is called thermo EMF. Then solar cells. So solar cells is also another method of producing electromotive force. Then the fourth method is electromagnetic induction, electromagnetic induction method. So these are the, so in electromagnetic induction method, EMF is produced as a result of change in the magnetic flux with respect to time. So these are the 4 methods of producing EMF. Now we are going to see how to produce induced EMF. Induced EMF is produced by electromagnetic induction method. So electromagnetic induction method is the method of producing induced EMF. In this, magnetic flux, when it changes with respect to time, EMF is produced. So magnetic flux is given by the formula pi b is equal to B A cos theta. So this expression tells that magnetic flux is the product of magnetic field, area and theta angle. So by changing any one of this factor, magnetic flux changes. When any one of this factor is changed with respect to time, then EMF is produced. So there are 3 methods of producing induced EMF. So what are the 3 methods? First method is by changing magnetic field. By changing magnetic field, we can produce induced EMF. So when magnetic field is changed, magnetic flux will change. When magnetic flux changes, it will produce EMF. Then by changing the area, enclosed by the coil, we can produce induced EMF. Then the third method is by changing orientation of the coil. Orientation of the coil. So these are the 3 methods of producing induced EMF. So in this part, we are going to see the 3 methods of producing induced EMF. Students, we know magnetic flux is given by pi b is equal to B A cos theta, where B is the magnetic field, A is the area and theta is the angle between the magnetic field and normal to the area. So now when this magnetic field changes with respect to time, then magnetic flux will change with respect to time. So according to Faraday's laws of electromagnetic induction, the magnitude of the induced EMF is given by epsilon is equal to minus plus d by b by dt. So I put plus here because we are considering only the magnitude. Now when I substitute this formula, we will have induced EMF is equal to d by dt of B A cos theta. When this area and the magnetic field are perpendicular to each other, then theta is equal to 0. At that time, cos theta will become 1. So induced EMF is given by epsilon is equal to d by dt of BA. Since area remains the constant, expression for induced EMF is given by epsilon is equal to A into dB by dt. So this is the expression for induced EMF by changing the magnetic field. Actually, we have already seen this in Faraday's experiment. So what are the different types of experiments conducted by Faraday? So we are having a coil of wire connected to a galvanometer. So this is a magnet, North Pole, South Pole. So in the first part of the experiment, either the circuit has to be moved far away or close to the magnet, or this magnet has to be moved far away or close to the coil. Whenever there is relative motion between the circuit and the magnet, a deflection is produced because of the induced EMF. So by moving this circuit or the magnet, what we are actually doing, we are changing the magnetic field with respect to time. So as I move the magnet far away from the circuit, magnetic field goes on decreasing. Or if I move the magnet close to the circuit, magnetic field is increasing. Keeping the magnet constant, when I do the experiment, same experiment, by moving the circuit far away or close to the magnet, again magnetic field changes. Because of this change in the magnetic field, magnetic flux will changes with respect to time. So an EMF is induced. This is how we produce induced EMF, by changing magnetic field. In another type of experiment, what we are doing, this is a coil of wire connected to the galvanometer. We are having another coil of wire. This coil of wire is connected to a battery through a key battery. So when I form the circuit, that is, when the key is closed, current will flow through the coil. So magnetic flux is linked with the coil. Magnetic flux is also linked with the circuit. So the galvanometer shows deflection. So by closing the key or breaking the key, what we are doing, we are producing magnetic field, or the magnetic field is stopped. So at that time, what will happen? Magnetic field linked with the coil, it changes. Because of the change in the magnetic field, magnetic flux changes. Because of the change in the magnetic flux, induced EMF is produced. So the Faraday's experiment tells that when magnetic field changes, magnetic flux changes. When magnetic flux changes with respect to time, an EMF is produced. So this is how induced EMF is produced, by changing the magnetic flux. So the next method of producing induced EMF is by changing area enclosed by the coil. So by changing the area enclosed by the coil, we are going to produce change in the magnetic flux. So when magnetic flux changes with respect to time, and EMF is induced. So next method is how to produce induced EMF by changing area enclosed by the coil. So magnetic flux is generally given by phi B is equal to B A cos theta. Since it is a coil, if you consider coil, if it will have n terms, so you will have NAB cos theta. When n takes the value 1, then you will have phi B is equal to BA cos theta. If B and A, that is magnetic field and area, are perpendicular to each other, then theta is equal to 0. So when theta is equal to 0, this cos theta takes the value 1. At that time you will have phi B is equal to BA. So according to Lenz's law, according to Faraday's laws of electromagnetic induction, induced EMF is given by the magnitude of induced EMF is given by d pi by dt. That is d by dt of BA. Since we are going to keep the magnetic field constant, induced EMF is given by B into dA by dt. So change in area with respect to time. So to produce induced EMF by changing the area enclosed by the coil, we are having a special arrangement here. So we are having a rectangular coil. So this is a rectangular coil. Rectangular coil. This coil is kept in the presence of magnetic field. So the presence of magnetic field is represented by several crosses. Every cross represents magnetic field line perpendicular to the plane of the blackboard. So we are having a coil frame of rectangular shape. In this frame, we are having arrangement. This side of the frame can move over this frame. So this frame AB is a rod. This AB, a rod of length L, can slide over this rectangular shaped frame. Now let this rod AB moves with the velocity V. Moves with the velocity V. That is pulled towards left. When it is pulled towards left with the velocity V, then distance moved by this rod AB, the certain interval of time is L into V. So L into V is the distance moved by this rod. So the changing area, initial area is this much. This shaded portion is the changing area. So changing area dA is equal to LV. What is equal to area CABD. The CABD is the changing area. Let this changing area happens in a time of dt. Therefore, changing area with respect to time dt is equal to LV. So substituting this value here, we will have epsilon is equal to B into dA by dt. So change in flux, change in area with respect to time. So if you take this time as 1, then this expression will become dA by dt is equal to LV. So epsilon is equal to BLV. So induced EMF epsilon is given by d by B by dt is equal to B into dA by dt. So dA by dt is equal to, or change in flux, epsilon is equal to, change in flux is given by d by B is equal to dA. So d pi by dt is equal to BLV. So this is the expression for the induced EMF. So induced EMF is given by BLV. So this is how EMF is produced by changing the area enclosed by the coil. So by changing the area enclosed by the coil, we can produce induced EMF. This induced EMF produced by changing the area enclosed by the coil is also called as motional EMF. And the expression for the motional EMF is given by epsilon is equal to BLV. So next method of producing induced EMF is by changing the orientation of the coil with respect to the magnetic field. So we are going to change the orientation of the coil with respect to the magnetic field. So this method is the method of producing induced EMF. It is a commercial method of producing induced EMF. So this method is applied in generators. So this method is method of producing induced EMF which is commercially used. So in order to explain how to produce induced EMF by changing the orientation of the coil with respect to the magnetic field, we are going to consider a rectangular coil containing n turns, area A, kept in a uniform magnetic field. When it is kept uniform in the magnetic field, let the plane of the coil is perpendicular to the magnetic field. Initially, the plane of the coil is perpendicular to the magnetic field. When the plane of the coil is perpendicular to the magnetic field, the flux linked with single turn of the coil is AB cos theta. Since the coil is having n turns, total magnetic flux linked with n turn of the coil is given by N AB cos theta. So according to Faraday's law, induced EMF is given by minus d by v by dt. So substituting this value, you will have minus d by dt of NAB cos theta. NAB cos theta. So that is induced EMF is given by minus NAB into d by dt of cos theta. So what is theta here? The angular displacement of the coil. So in this method, we are going to rotate the coil in the magnetic field. So when we rotate the coil, the angular displacement of the coil is represented by theta. So theta here, theta is equal to angular velocity into time, angular displacement. So substituting this value, you will have induced EMF is equal to minus NAB into d by dt of cos omega t. So that is equal to minus NAB. When you differentiate this, you will have minus sin omega t into omega. So you will add epsilon is equal to minus into minus will become plus NAB omega into sin omega t. So when this coil is rotated with a constant angular velocity NAB omega are constant. So this can be replaced by a single constant. So you will have induced EMF is given by E naught into sin omega t. So this is the expression for induced EMF. So where E naught is the maximum EMF, this omega t is the angular displacement. So now we are going to explain how this induced EMF is produced in the coil when the coil is rotated in the magnetic field. So further, in order to explain that, we are going to consider a magnetic coil. So this is magnetic field. In this magnetic field, we are keeping the coil like this. So now this coil is rotated about an axis perpendicular to the magnetic field. So this is the top view. So when I draw normal, this is phi b, plus through the coil is phi b. So phi b in this case is b into a, since cos theta is equal to 1, theta is equal to 0. Now when this coil is rotated, so I am rotating this coil. When the coil is rotated in the anti-clockwise direction. Now let this be the position of the coil. So now this coil is rotated about an angle omega t. Now I can resolve this phi b into two components. This is phi b cos omega t. This is phi b sin omega t. So now this phi b is given by b a cos omega t. This component has no effect on the magnetic flux because this is parallel component, this is vertical component. So phi b is equal to ba cos omega t. Since the coil is having n turns, n into phi b is equal to nab into cos omega t. So this is how we get expression for the magnetic flux, nab into cos omega t. So this is how we get the expression. Now let us see how the induced EMF varies with respect to theta, because when theta changes, induced EMF will also change. So now we are going to see how the induced EMF changes. So expression for induced EMF is given by epsilon is equal to E naught into sin omega t, where E naught is the maximum induced EMF. This is equal to nab omega. This omega t is equal to angular displacement theta. So now let us consider a coil of wire rotated in a magnetic field. So we are having, so here there is uniform magnetic field. Initially, we are keeping the coil whose plane is perpendicular to the plane of the magnetic field. So magnetic field and the coil are perpendicular to each other. At that time, omega t is equal to 0. Omega t is equal to 0. So I can draw this south pole here. So we are going to plot a graph by taking omega t along the x-axis and induced EMF along the y-axis. So this is omega t along the x-axis, induced EMF along the y-axis. Initially the induced EMF is 0. Now this coil is rotated in the anti-clockwise direction. When the coil is rotated through 90 degrees, so So I am rotating the coil through 90 degree. So these are perpendicular to each other. When it is rotated through 90 degree, angular displacement is equal to pi by 2. At that time, magnetic field and the plane of the coil are parallel. When magnetic field and the plane of the coil are parallel, then the angle is rotated through 90 degree. At that time, so case 1a, E is equal to E naught into sine 0. So sine 0 is 0. So we are marking here 0. Then B, next position. This is B, position B. In position B, the coil is rotated through 90 degrees. So you will have E is equal to E naught into sine pi by 2. That is equal to E naught. So induced EMF is maximum. So this is E naught. And this is minus E naught. Again, the coil is rotated through 90 degree. Again, when the coil is rotated through 90 degree, the plane of the coil becomes perpendicular to the magnetic field. So, C, position C. So, here omega t is equal to 0, omega t is equal to pi by 2. The third position, E is equal to E naught into sine pi. Sine pi is 0. So again, the induced EMF becomes 0. Again, the coil is rotated through 90 degree. So when the coil is rotated through 90 degree, then omega t is equal to 3 pi by 2. So when the coil is rotated through 90 degree, we will have V. Here omega t is equal to pi. Here omega t is equal to 3 pi by 2. So at that time E is equal to E naught into sine 3 pi by 2. Sine 3 by 2 is minus E naught. So we will have minus E naught. This is 0 pi by 2 pi 3 pi by 2 and again 2 pi rotated through 90 degree. Again, when the coil is rotated through 90 degree, now the coil comes to the initial position. At that time we will have E is equal to E naught into sine 2 pi. Sine 2 pi is equal to 0. So when I plot the curve, I will get a curve like this. So when you see the induced EMF, the induced EMF varies in the same way as that of a sine wave. So the induced EMF varies in the same way as that of a sine wave, and hence this EMF is called as sinusoidal EMF. So when we produce induced EMF by changing the orientation of the coil with respect to the magnetic field, the induced EMF changes in the same way as that of a sine wave, and hence this EMF is called as sinusoidal EMF. So the general expression for the induced EMF is given by epsilon is equal to E naught into sine omega t. So when this EMF is given in an electrical circuit, it will produce a current, and the expression for the current is given by I is equal to I naught into sine omega t. So this current is called as alternating current, and this voltage is called as, or EMF is called as alternating voltage. Why it is called as alternating current or alternating voltage? It alternatively changes its magnitude and direction in an electrical circuit. So this type of current and voltage are called as alternating current and alternating voltage. So these are the three methods of producing induced EMF. So induced EMF is produced by changing magnetic field, by changing area enclosed by the coil, and by changing the orientation of the coil with respect to the magnetic field. So the induced EMF produced by changing the magnetic field is actually the experiment conducted by Faraday. So the induced EMF produced by changing the area is called as motional EMF, and the expression for the motional EMF is given by epsilon is equal to B and V, and the expression for induced EMF by changing the orientation of the coil is given by epsilon is equal to E naught into sine omega t. So thus we see that there are three methods of producing induced EMF.